Hi, welcome to this virtual field trip of the red rocks of the Sedona area. Sedona is about 2 hours north of Phoenix. It's in central Arizona. It's a little less than an hour south of Flagstaff. And Sedona is very famous with tourists and with geologists because it has these spectacular exposures of red rocks, which actually are not that well understood. The feature behind us is called the Mogollon Rim, M-O-G-O-L-L-O-N Rim. And it's the topographic feature that's formed essentially an escarpment held up by Permian rocks. And all the rocks behind us that you can see in this view are all Permian in age. There are other Paleozoic rocks below us, down to the Devonian, and there are basalts and things like that on top of the Paleozoic rocks. But the red cliffs themselves are mostly Permian. Traditionally, these rocks were always called the Supai Formation, correlated with the Supai, the red rocks in the middle of the Grand Canyon. The precise correlation between those units, though, has not always been very well known. The upper part is a cliffy sandstone, and then you can see just the start of some more ledgy rocks down below. The rocks I'm standing in has a lot of slope-forming siltstones and things like that. And so traditionally they've used three letters, Supai A, Supai B, and another unit which you can't see from here called Supai C. The light-colored rocks on top is the Coconino sandstone, and it is equivalent to the big cliffy unit that sits above the Hermit in the Grand Canyon. It has the same character here as in the Grand Canyon. It's a quartz sandstone with large-scale crossbeds that are interpreted to be Aeolian in origin. So this is thought to be just essentially a continuation of the big sand sheet that deposited the Coconino in the Grand Canyon. An interesting rock in the sequence, about 2/3 of the way up the cliff, is there's a little thin layer of gray limestone called the Fort Apache limestone. It's a marine limestone. It's Permian in age. It's actually been recently redated as Leonard in age with fossils. And so we know the age of those rocks. And so, that's a marker. That unit thickens off to the southeast and eventually becomes part of all the Permian and Pennsylvania units that are down in southeastern Arizona in a big basin called the Pedregosa Basin. So that unit comes in here and thins and thins and thins, and not very far that way, it's gone. And so although that's a nice unit to correlate from here to the southeast, it doesn't help us between here and the Grand Canyon, because this unit is not present in the Grand Canyon. So one of the issues is that the units are thickening to the southeast towards the Pedregosa Basin, and then in the Grand Canyon, the units are thickening to the west towards Nevada. And between those two is a little area called the Sedona Arch, which we're in. And it evidently was an area that's just subsided a little less, or maybe it was a positive area at times. And so the units from southeast Arizona lap out against it, and the units from the Grand Canyon come in, and there's a facies change in here. So it's really hard to try to correlate the units in the Grand Canyon with the rocks in here. As we go along today, we'll talk about what some of those issues are and some of the ways we've approached it. We've done a lot of detrital zircon work on these sandstones in here to try to better constrain what the correlations are with the Sedona rocks and the Grand Canyon. It's a little amazing. It's this very famous place with geologists, and we don't quite understand it. We're at an overlook called Yavapai Point. It's south of Sedona and north of the village of Oak Creek, and it provides you a really nice overview of the entire area of the Red Cliffs. As you look at these cliffs, you can see there's an upper white cliff, and then a middle kind of tan or reddish tan cliff, and then a lower series of ledges as if the rocks are just becoming a little bit more slope forming. In here, the sequence is the upper unit on top of the cliffs is the Coconino sandstone of Permian age. And then once you start hitting the tan layers, the reddish layers, then we started using the term Supai traditionally in here. The cliffs are mostly held up by the Coconino Sandstone and Supai A. The city of Sedona is actually in around Supai B. It's a lot of slope forming stuff, so as you drive through Sedona you see lots of red road cuts, and that's all the middle part of the Supai in here. You don't see it in here very well, but on top of these cliffs in the background there are some basalts, some tertiary basalts. And so that's kind of the sequence in here, tertiary basalts. There's actually Kaibab limestone, which is the highest Permian unit in this part of Arizona, and then Coconino, and then these rocks that have traditionally been called Supai. You can see that erosion has done a lot of really nice sculpting of the cliffs, and so there's a lot of visual interest in here. To some extent, cliffs, if they don't have joints, tend to be kind of boring, but the fractures in the rocks, the joints, give you little notches and little places where the cliff sticks out more, or it has little recesses. So joints are always a really important part of any landscape. It adds a lot of texture to the cliffs especially. We're at another geologic viewpoint between the village of Oak Creek and Sedona, a place called Yavapai Point. And the feature here is this cliff face behind us, which has a really cool relationship, so cool you might call it Coolosaurus. And what you can see is the very top of the hill is Coconino Sandstone, and below that are the red rocks of the Supai group. And in the middle of the cliff is a really obvious white layer of rocks. The setup for this is in the Grand Canyon, you have the Supai, and then you have the Hermit, and then the Coconino is on top of the Hermit in a very sharp contact. In here, the bottom of the Coconino is not a sharp contact, and what you can see is that first little thick layer of sandstone in there is the first layer of Coconino that got deposited in here, and then the environment went back to the red rocks, and then eventually another one of those layers of Coconino, and then it went back to red rocks for a little bit, and then finally the Coconino came over the top. Remember that the Coconino is an Aeolian sandstone, so those are basically sand dunes blowing in across a nearly sea level mudflat, or sand in some places. And so in here it's very clear that those two units are like this, the Coconino and the Supai. And so it's a case where these rocks have got to be younger, the red rocks have got to be younger than what you see in the Grand Canyon, because there it's a sharp contact, here it's a gradational contact. So that was a clue in here that there are some younger rocks in here than are present in the Grand Canyon. For that reason, some people, including Ron Blakey, have named this unit in here the Schnebly Hill Formation, and think that you should not use the term Supai for it. Traditionally, this whole package of red rocks has been called the Supai, but Ron thinks that this upper unit should have its own name. And one debate is whether the Schnebly Hill should just be another formation in the Supai, or whether it's something different, and we'll talk about that a little bit later. But the interesting thing in here is to try to envision the environments. You have this mud flat. We know that we're right at sea level because at the bottom of the cliff, there's a gray ledge of Fort Apache limestone. So we know we're at sea level. That's a marine rock. But you're very close to sea level, and then at some point the sand dunes kind of come in and get deposited over the top. And so you have a mud flat, and then the first bit of sand dunes comes over, and then ends, and then the top of those sand dunes get truncated, and you deposit more of the red sandstones, and then later more and more. So it's a beautiful example of how one formation can grade into another formation, just a change in the environment. And it's also interesting to realize this tells us that the Coconino sandstone was deposited at nearly sea level, because it's got marine rocks not very far below it, and we don't envision there are a lot of changes in here during that time period. In the area of Sedona, there are a lot of really interesting geologic relationships. One is this flat mesa in here that's capped by basalts. And what you can see is in the distance, you have the full sequence of Paleozoic rocks. You have the Supai, you have the Coconina, you have the Kaibab, and then in the distance there's some little basalts as well. But in the foreground, you can see that the basalts sit down on the Supai. Not only that, you're missing the upper cliffs in the Supai. So the implication in here is that when that basalt was erupted on the surface, you had already eroded off the upper Paleozoic rocks. So when that basalt was erupted, the Mogollon Rim had to already be here, because the Paleozoic rocks are gone here, but they're still there. And so you can, in here, using the ages of the basalts and some gravels, you can kind of map the sequence of the evolution and the erosion back of the Mogollon Rim with time. We're now at a site called Grasshopper Point. We're within Oak Creek Canyon, and Oak Creek is just back there where the sycamore trees are. It's, you may be able to hear the running water. There's also wind. The red rocks of Sedona have traditionally been referred to as Supai, to correlate them with the red rocks in the middle of the Grand Canyon, Pennsylvanian Permian Supai Formation, then subdivided into formations that made it the Supai group. The Supai in the Grand Canyon has been assigned to 4 formations: Wattahamagie, Manicacha, Wescogamy, and Esplanade. Ed McKee of the USGS and other places did that work. When he came to Oak Creek, he called it Supai, but he didn't feel comfortable enough that these rocks matched the rocks in the Grand Canyon to apply those names here. And so what he did instead, he just assigned it to Supai A, B, and C. And we can see all of those 3 units from here. The cliff at the top, we're seeing the very bottom of the sandy A unit. This slope in here with the slope and ledges, that's B. And the light-colored calcareous sandstones in here, that's Supai C. So there's A, B, and C. And that terminology has been used for a long time. One of the issues in here is that since you have a hard time correlating this to the Grand Canyon, what names do you use in here? Some people think, and based on a lot of study, that these slope-forming rocks in the middle is actually equivalent to the Hermit Formation, and so they've used the name Hermit in here. I'm not a big fan of that, but it's widely used. If you read material about Oak Creek Canyon, you'll commonly see that referenced as Hermit. We're a long way from the Grand Canyon. The Hermit is thinning in this direction, and so it has to change its thinning direction to have this much Hermit be here. And there's also some issues about the age of these rocks, and are they the same age as the Hermit, and things like that. So the people that want to use the name Hermit in here, like Ron Blakey, they recognized if this is Hermit, then Supai is only the stuff below you, because in the Grand Canyon you have the Hermit and you have the Supai. And then anything above the Hermit cannot be Supai, because it's physically above the Hermit Formation. And so he proposed a new name, the Schnebly Hill Formation, named for Schnebly Hill, which is that way. And a lot of people in this area use those names. They use Hermit and Schnebly Hill. Other people don't like that correlation. Another group worked in here and they said, oh, we found Hermit, but they found Hermit way the heck up in A. Another guy that worked in here for the Arizona survey thought, from correlating these rocks to those rocks further east, that this was much older than Hermit should be. And so he did not want to use the name Hermit in here. And that's an unresolved problem. There's still a controversy about what you do in here. We're trying to do some work with fossils and detrital zircons to try to answer some of this question. In here, we came in to do detrital zircons, so what we're doing is taking sandstones, grinding them apart, and getting the uranium-lead ages of individual zircons or spots in zircons. And so we collected rocks in C, we collected rocks at the bottom and top of B, and we collected rocks at the bottom and most of the way up A. Those data are permissible with this being Hermit, but just barely. The thing that's interesting is in the Grand Canyon, when when we talked about these rocks for decades, we always said these red clastic rocks came from an ancestral mountain range mostly in Colorado and Utah, to some extent in northeastern Arizona, called the Ancestral Rockies. And that's a Pennsylvanian Permian mountain range. People think it's more or less related to the collision of Africa and South America with North America. And so the assumption for years was that all this red detritus came off the Ancestral Rockies. The Ancestral Rockies has a bunch of rocks in it that are 1.7 billion, 1.4 billion, and that's about it. When people came in and started looking at the Grand Canyon and doing detrital zircon work, what they found out, there was a whole bunch of 1 billion-year-old zircons in here, which is Grenville age, not very common out here, but really common in the eastern coast, the eastern US. And also there were like 500 million-year-old zircons, 450 million-year-old zircons here. And we don't have any of those rocks around. The Ancestral Rockies don't have any of those rocks, but the Appalachians have a ton of those rocks. And so the big implication of the first detrital zircon studies that were done by Bill Dickinson and George Garrels was that there was a bunch of ancestral rocky sediment in here, but there was even more sediment that had come off the Appalachians and had to be transported across nearly the entire continent into here to get those sediments in here to Western North America, southwestern North America, where we are here. So in the Grand Canyon, there's a detrital zircon influx of about 500 million-year-old zircons at the Hermit. And below that, it's mostly 1 billion. So in here, we see an influx of 500 million-year-old zircons, but it's a little higher up the section. And so right now, I'd say it's still a little dodgy whether this could be Hermit or not Hermit. We're still looking at that. We're going to do a study of paleontology the next canyon over, Fossil Creek, and see if we can't use fossils to constrain this section a little better. One of the things about this section that's Supine B, and I'll just use that terminology, is there are conglomerates in there. And when you track this interval with the conglomerates to the east, it has fossils in it that are really low in the Permian or are the Pennsylvanian Permian boundary. And that's not permissible to be Hermit. So there's a conflict here between the stratigraphic evidence, where people tried to bring the stratigraphy in from the Grand Canyon, versus the paleontology evidence and perhaps the detrital zircon evidence. We're still trying to resolve all that. One of the interesting things about that whole scenario of all this material coming from the Appalachians is, remember what the Appalachian Mountains represent. They represent a collisional mountain belt, not between the subcontinent of India and the rest of Asia. It's a collisional mountain belt between North America, Africa, and South America. So it's a huge continental collision. And so you likely made a really big mountain belt, and now that mountain belt has a bunch of metamorphic rocks sitting at the surface, the Appalachians. And so all that material that was on top of those metamorphic rocks had to get stripped off and go somewhere. And so it was presumably transported west along big rivers, and then transported, south and north by ocean currents, winds, things like that can move sediment up and down the coast.